Hello, welcome to Econometrics Melody. In this video, we'll discuss about the matrix notation of linear regression equations. And first of all, let us explore some useful topics, and that is dot product. If we have a vector in two dimension, vector A, this is represented by x1, y1, and vector B, it has its coordinate is x2, y2, and A modulus of vector A, this is given by the square root of x1 square plus y1 square. This is the length of vector A. Similarly, the length of vector B, or the modulus of vector B, this is again a square root of x2 square plus y2 square, and therefore the dot product of vector A and B, this is given by the product of the modulus, their respective modulus, into cos theta, and where theta is the angle between vector A and B, and this can be expressed in their coordinate forms as the sum of the product of the one-to-one element, that is x1 into x2 plus y1 into y2. We are going to make use of this dot product in order to denote the matrix notation of linear regression equations. So if we have two vectors A and B, the dot product is simply the projection of one on the other. So here it is the projection of B on A if we take A at first, and this is the projection of B on A. Otherwise, if we take B as first, then this much is the projection of A on B, and theta is the angle between vector A and B. So if this theta is equal to 90 degrees, that is what we mean by is the orthogonal vectors, that is the vectors are orthogonal, the angle between them is 90 degrees, and in that case the value of cos 90 degree, this is equal to 0. Therefore the dot product of the vectors A and B, this is equal to 0, and therefore x1 into x2 plus y1 into y2, that is the sum of the product of one into one element, this is equal to 0. And this property has useful implication in order to identify the two variables or vectors is orthogonal, and if their dot product is equal to 0, we call that the two vectors or variables, they are orthogonal. Similarly, in classical linear regression model, if the independent variable, the dot product of each of the independent variable with the error term, if it is 0, then we call them as orthogonal, and we have this assumption that the independent variable and the error term, they are orthogonal, they should be orthogonal. Similarly, when theta is equals to 0, then the value of cos theta, this should be equal to 1 because cos 0 is equal to 1, and in that case we call the vectors as parallel vectors, and A vector dot B vector, their dot product is simply the product of their individual modulus, and which can again be expressed as x1 into x2 plus y1 into y2. So when the vectors are parallel, we can express them, or we can express one vector is the scale of the other vector, and this property is in some way useful in order to identify, in order to calculate the eigenvalues and eigenvectors. Here matrix A, it transforms the vector x, and the transformation is equivalent to simply scaling the vector x. So the internal process involved to calculate either the eigenvalues or the eigenvector is equivalent to the property of the parallel vectors, because here the vector x when transformed is equivalent to simply scaling this vector by this value lambda, and the property of parallel vector is in one or the other way used in eigen decomposition of a matrix. We have a matrix A and a eigenvector matrix C. So this is again equal to C and the diagonal matrix with eigenvalues as its elements, and if we operate it properly, we get the eigenvalue decomposition of matrix A. Now let us move into today's topic, that is matrix notation of linear regression equations. So we have y is our dependent variable, and we are taking only 3 observations for the simplicity. And we have two independent variables, x1 and x2. So for 3 observations, we are going to get 3 equations, and they are expressed in this form. So each observation of y can be expressed as some constant plus some scale of x1 plus another scale of x2 plus the residual term. And if we collect it, or if we present it in different forms, so this is equal to 4, 3, 2. So we have beta 0 as common, so we write it as the factor of 1 plus, and we have again beta 1 is common, so we have 2, 4, 7, and then beta 1 plus again beta 2 is common, 3, 6, 9, and then we have beta 2 plus the error term. So here our dependent variable, this is equal to the sum scale of the independent variables. If you look at it, we are simply scaling the first variable by b1 and scaling the second variable, independent variable, by b2, and the constant term is beta 0. So we are scaling the independent variable in such a way that we try to approach very close to our dependent variable. So this is the main idea behind the linear regression model. Now let us replace these observations with their variable notation. So 432, this represents our dependent variable y, and the column vector of 1, this is represented by vector I, beta 0 plus, and 247, this is our first independent variable x1, and 369, this is our second independent variable scaled by beta 2 plus, this is our error term e1, e2, 3, this is the vector of our residual or error term. And if we ignore the error term, so up to this point it seems like it is again a dot product, which we have seen in our introduction. So this is the dot product of variable and the scalar. So here I, x1 and x2, they are variable or vectors, and beta 0, beta 1 and beta 2, they are scalar. Therefore y, this is equal to, now let us segregate the vectors and scalar to form the vectors of the vector. Here I, x1 and x2, this is the row vector of the vectors, while beta 0, beta 1 and beta 2, this is the column vector of the scalars. That is our unknown parameters plus the vector e. Now if we further operate it, y is equal to, now the row vector of the vectors is its elements. This is in fact a matrix because we have n number of observations. Each vector I, x1 and x2, they are of order n into 1. So this is our matrix. Let us write it as matrix X. So this is equal to matrix X, and the vector of the estimates, that is unknown parameter. So let us write it as B, and plus the residual error term or the residual term. So this is our general notation or the matrix notation of the linear regression equations. So here y is of order n into 1, x is of order n into k, the unknown parameters beta, so this is of order k into 1, and the residual term or the error term is of order n into 1. And if we further operate it, n into 1 and this k into k, so when we multiply it, we get the vector of order n into 1 plus n into 1. So this is our error term, and this is our y cap, and this is our y. So in matrix notation, the linear regression equation, it is represented as y is equal to x b plus e. So where y is our dependent variable and it contains n number of observation, and this is of order n into 1, and where our x, the first column, it contains the vector of 1, and this is also of order n into 1. And similarly we have, let me write it as I, and this from second column onwards we have our independent variables. Let me write it as x1 all the way to x k minus 1, and each of these independent variables, they are of order n into 1. So this matrix X, generally called is the matrix of independent variables. This is of order n into k, and we have our unknown beta, and this is of order k into 1, beginning from beta 0 all the way to beta k minus 1, and the residual or error term, this is of order n into 1, and we have n number of observations, that is the error terms n into 1. Therefore finally we have y, this is equal to x b plus e. So y is equal to x b plus e. This is our matrix notation of the linear regression equations. So in the real world, we have the observations for this dependent variable, we have the observations for independent variable, and we have to estimate this beta so that the error is minimized. And where xb, this is simply the linear transformations of our independent variable. So we scale these independent variables in such a way that the final result, it approaches very close to our dependent variable. So this is it for this tutorial. Thank you very much for your time. Thank you very much. Econometrics Melody.